Hi, I'm Jake Covington.
And I'm Ty Cosley, and this is our senior design project for our undergraduate electrical engineering degree at the University of Florida.
The Gator Unmanned Aerial Vehicle Autopilot System, or GUAVAS, is a waypoint navigation-based autopilot system for quadrotor vehicles.
The system consists of three main parts: the quadcopter, the ground station, and the user transmitter.
GUAVAS has the following features: autonomous waypoint navigation via pre-planned mission and queue ground control, the off-the-shelf ground station that we've chosen. Manual versus autopilot flight mode, which are easily switched between using the transmitter. Multiple control modes via cascaded PID loops. These include angle mode, or self-leveling, rate mode, or acrobatic, and velocity mode, which is used in the autopilot only. It also features a return to home emergency function, which allows the user to simply flip a switch and have the quadcopter return from where it took off from. High bandwidth state estimation and inertial navigation using two extended Kalman filters, the use of common MEMS sensors to drive down cost, real-time telemetry data to a ground station dongle that we've designed via RF link using the lightweight but common Mavlink protocol. It works with any transmitter or receiver up to 8 channels. Portability between multiple airframes due to the standard hole spacing on the PCBs, a high-density PCB to provide powerful processing yet small and compact size, external peripheral connectors and extra processor I/O to allow for future development, low power with the ability to draw from multiple sources. This includes a 3S or smaller LiPo battery, USB, or external 5-volt power supply, usually through a BEC. GUAVAS also has the ability to control an external camera gimbal while the autopilot is active, though this is not included in this project at this time. The quadcopter consists of a commercial off-the-shelf carbon fiber frame, Tiger brand motors and electronic speed controllers, 7.5-inch plastic propellers, a 3S LiPo battery, and the custom GUAVAS autopilot board. GUAVAS is based off the STM32F4 ARM Cortex-M4 microprocessor. This platform was chosen due to its ARM instruction set and dedicated floating point unit, which are needed to perform the large matrix algebra operations used in the extended Kalman filters. It was also chosen due to its package size and multiple peripherals that are used to interface with the sensor suite. The autopilot board contains 6 main sensors: an MPU 6000 integrated accelerometer gyroscope, an HMC 5883 compass, a NEO M8 GPS, an MS 5611 barometric altimeter, and an LV Max Sonar EZ0 ultrasonic rangefinder. It also contains 32 kilobits of EEPROM for storing flight parameters, as well as a 900 MHz RF module for telemetry. All external signals such as the USB, the PWM signals, the GPS UART, and the compass I2C are buffered through their respective ICs in order to ensure proper signal integrity across the PCB. They also serve the purpose of isolating these parts from the rest of the board in case of an overcurrent condition or other fault that they might cause. The Autopilot PCB was designed and manually routed using dip trace and then manufactured at Bay Area Circuits. For populating the PCB, we used a homemade reflow oven built using a standard toaster oven and a Zallis reflow controller. By using a stencil, we were able to apply solder paste, hand place all the surface mount parts, and then reflow the board. This was done to reduce overall size, but it also allowed us to solder the leadless QFN packages for a few of the sensors.
The ground station consists of 3 components: the ground station dongle, a computer, and the ground station software. The ground station PCB was designed and manually routed using dip trace and then manufactured using OSHPARC. The same refill process used for the Autopilot PCB was used for populating the ground station PCB. The ground station dongle has 2 major components: the Lynx RF transceiver and the FTDI USB to UART chip. Both of these parts are used to interface the serial communication between the quadcopter and the ground station software. The selected transceiver modulates the UART transmit signal to a high-frequency RF signal and back the other way for the receive signal in order to establish the long-distance serial communication between the Autopilot board and the ground station. The board also has ESD and overcurrent ICs to protect against fault conditions.
System 1 is now in and standing by.
Q ground control software can run on Windows, Mac, and Linux. The software communicates to the quadcopter using an efficient packet-based language called Mavlink. The telemetry information sent to Q ground control is the UAV roll, pitch, yaw, altitude, and GPS latitude and longitude. Other information that is sent includes number of GPS, satellites, battery level, and current flight and control modes. Q ground control displays a virtual horizon and compass, an altimeter, a real-time GPS path overlaid on satellite imagery, and system information along the top of the screen. As you can see, all of this is displayed in real time as the user moves the UAV. Now we will show a demonstration of the Autopilot capabilities. As the quadcopter takes off, the quad ascends to a set altitude. Due to the ground effects during liftoff, the vehicle might move away from the home waypoint. Once the correct altitude is attained, you will notice that the vehicle will move back to the home waypoint before it begins the mission. At this point, the quadcopter calculates the appropriate heading for the first waypoint and will yaw in that direction. Once the vehicle is within the bearing limit, which decreases as the quad reaches the waypoint, the autopilot will command a forward velocity in the X direction. To keep the vehicle on course, a velocity of 0 is commanded in the Y direction. The autopilot considers the waypoint to be reached when the quad is within a set radius. For this flight, the waypoint radius is set to 1 meter.
The navigation scheme used in GUAVAS consists of two extended Kalman filters. The first implements an attitude heading reference system using the accelerometer, gyroscope, and magnetometer values. The second implements an inertial navigation system using the accelerometer values and GPS coordinates. By properly tuning these two filters, an extremely accurate estimate of the UAV's orientation and position in the inertial frame can be obtained. These estimates are then used in the control section as feedback. The control structure for GUAVAS is entirely made up of cascaded PID controllers. A velocity is commanded which is sent through a velocity PID controller. This output is then fed through the chain of angle and rate controllers. The altitude is controlled using an entirely separate PID that has a feed-forward term related to the hover point of the vehicle. The outputs of the last PIDs are then sent to a motor mixer that calculates the correct PWM signal to send to each motor.
Once GUAVAS reaches its final waypoint, it returns to the home location and descends to end the mission.
System 1 is now in and standing by.